would like to introduce a new self-supervised learning framework named ALICE, designed for 3D medical image analysis tasks. ALICE harnesses the power of contrastive learning and masked image modeling. It also incorporated several novel improvements to enhance both these aspects. First, existing contrastive learning methods simply treat image patch samples which may depict totally different anatomical information from the same CT volume as positive pairs, while considering samples sharing the same semantic content class, but from another volume as negatives. ALICE leverages the consistent anatomical structures across different volumes and addresses the false positive and false negative pairs. Second, we address a critical oversight in existing methods that combine contrastive learning with masked image modeling. These methods tend to ignore the substantial semantic gap between masked views and augmented views. Differently, ALICE performs anatomical information alignment and thus crafts superior and more meaningful contrastive pairs. To begin with, ALICE employs a pre-trained SAM to locate the same anatomical body parts from two different volumes, which we term as inputs Q and K. Then 4 different data augmentations are adopted to generate 4 different views. Here, U and R denote random masking. The 2 masked views are first sent into the online encoder. As they pass through, their features, combined with mask tokens, are processed by an online decoder. This step aims to fulfill the objectives of masked image modeling, which helps to learn fine-grained local feature representations. As for the other branch, we begin with the 2 augmented, intact views. These views are not masked, preserving their full anatomical detail. They are subsequently processed by what we term the target encoder. At this juncture, the outputs from both the online encoder and the target encoder converge at a novel module named CASA to perform semantic alignment. After the alignment, ALICE maximizes the similarity between the high-level embeddings of the 2 views pairs from Q and K. At last, ALICE optimizes the intra-volume relationship by maximizing the similarity between views from the same volume. However, directly encouraging the masked views to have similar representations to the global views is unreasonable. So we adopt CASA module which matches the most relevant high-level semantics between masked views and intact views given the distribution of masked views' local patch texture. This leads to crafting more specific and aligned high-level features for self-distillation. ALICE is pre-trained on 2,000 unlabeled CTs from FLAIR 2022 Challenge. For segmentation task, ALICE is tested on 2 multi-organ segmentation datasets. We adopt 2 segmentation metrics of dice similarity coefficient and normalized surface dice. For classification task, ALICE is tested on a public COVID-19 diagnosis benchmark. We adopt the area under the receiver-operator curve as the evaluation metric. Compared with various V-based and CNN-based self-supervised learning methods, ALICE consistently outperforms these competing methods on FLAIR 2022 dataset. When tested on BTCV dataset, ALICE also outperforms all other self-supervised learning methods. Moreover, ALICE also outperforms other methods on COVID-19 diagnosis dataset. As an inter-scene evaluation, it reveals that ALICE has the ability to generalize to other scenarios. The qualitative results also demonstrate the merits of ALICE. We also evaluate the effectiveness of the proposed anatomical invariance modeling and semantic alignment. We integrated these components into a range of existing methods. Both these components, when applied independently or in tandem, have consistently demonstrated their mettle by bringing about tangible improvements across the board.